go straight into it? Yeah, good. Thanks for the introduction. Thanks everyone for being here. I'm going to take a slightly different perspective on thermodynamics and physics of energy today. We do work on resources and energy efficiency in the group, but I have to thank the organizers for telling me about it, letting me tell about a slightly different story today. And the sort of larger pitch here is a little bit, there's something interesting to make quantum thermodynamics interact with quantum foundations, and maybe that's a larger sort of question. And I want to address this specific question is, can intersubjectivity or objectivity emerge out of thermodynamics? Yeah? And so let's dive right in. We have two types of evolution, very broadly. This is, you're familiar with this in quantum mechanics. One is the unitary evolution according to the Schrödinger equation, which is reversible. And then usually we associate irreversibility in quantum mechanics at a basic level. We would say that's to do with measurement, right? Some interaction happens with the system, and on the level of the system that makes the dynamics irreversible. So the question that's long been asked in this field is, can we use reversible dynamics to explain this irreversible bit, right? Which is a way of saying, is there a solution to the quantum measurement problem or something like this, using the language of quantum mechanics? Yeah, we don't have to be quite as lofty, but that's a long-standing question. Wojciech Jurek, where I've taken this picture from one of his papers, for instance, has worked on this for a long time. And the second question is then, what actually gets measured in the process, both which system gets measured and what basis gets selected, right? And so to relate this to thermodynamics, let me put this very provocatively and naively, but just to get us maybe thinking about this. If you're thinking about this in a sort of very direct, simple way, you might wonder if the laws of thermodynamics actually hold under quantum measurement in the textbook sense, right? So if we were to measure a state up here, which is in superposition, we get out, let's take this to be in the energy eigenbasis, for instance, we get out a different state, and that seems like we've somehow violated the first law, yeah? At least at the very naive level, right? And we might also wonder about the third law, and maybe this is actually a little bit more interesting. So if a measurement takes place, what we would usually say, the system is then, if it's a projective measurement, it's in a pure state afterwards, and we can use some procedure. This could be a part of a unitary, for instance, over here. We could take the system to the ground state, so in some sense we could think of projective measurement as being equivalent to perfect cooling, right? There are caveats to this. I'm listing here a couple of papers that look at this in a lot more detail, but this is something we might wonder, are these things compliant, right? What I want to do is turn this in the other direction and ask, can we think of the measurement actually as a thermodynamic process, right? Which is to say, as a hypothesis, measurement is an entropy increasing transition towards an equilibrium state. That's what I mean by thermodynamic process. And we can look at this a little bit more detailed. So we'll have to get a better idea of what we want to achieve with the measurement side, and we want to specify what we mean by this transition and towards an equilibrium state. Yeah? So the first part leads us to this idea of objectivity, which we can define as a situation where a state of the system S exists objectively if many observers can find out the state of S independently and without perturbing it. Yeah? This is the notion that gives rise, if you're familiar with it, to quantum Darwinism, and has led to a few different sort of offshoots of that theory. Yeah? I want to pick a particular version of this, which is something called the spectrum broadcast structure. So what we're thinking of, if you want to look at the right-hand side over here first, we're thinking of a central system, which is surrounded by a bunch of external systems. And what we want to figure out is, if we think of these external systems as observers of the central one, can we find a situation of agreement as per the previous definition? And one way of thinking about this is we can define states of this form up here. These are quantum classical states with a particular structure among the observers, which are such that if you look at any of the observer systems, they will be in agreement about what state the central system is in among each other and with the system itself, right? And you can see this from here. What this requires is a particular structure here among the observers, where in particular the the support of the different measurements that the observers might make is non-overlapping, yeah? Which we could write as the fidelity being equivalent to this delta function here, where the k's correspond to the label the observer, and the j's label the measurement outcomes, or the m and n's label the measurement outcomes. Yeah, this is just a definition. We can actually notice that if we have some fairly strict requirement on this objectivity, which goes a little bit further than the original definition by Jurek, we need states of this form. Yeah, I don't want to motivate this in too much detail, but it has to do with being able to access information locally and Discord not getting in the way. And then we get to something called strong objectivity, which is defined in this paper down here, which leads to this state structure up here. Yeah. So the next part is the equilibration bit. So this is where we want to get to. This is the state of affairs that we'd like to get. The next question is, can we equilibrate to this? And I want to introduce this as well. We want to look in particular, we're thinking of the entire system as the universe, as a closed system, and we want to ask, is there a closed system equilibration that can occur where we end up in an SBS state? Yeah? And if you're not familiar with closed system equilibration, the picture to take here is a standard unitary evolution, but what we're interested in is the time average of this state, right? Which we write in this infinite limit of the time going to infinity. What we have in mind is actually this capital T being really short. So mathematically, we define this in a very long limit, but I should make this point. There will be Poincare recurrences and things like this, but the system is large enough that these are very far in the future, and this actually equilibrates. The idea is, the intuition is this equilibrates very quickly. We define it in the infinite limit, but just to be sure. And so if you think of this, so this is, for instance, an expectation value of some observable with respect to the expectation value in the equilibrium. What you would think is that the difference between these it can start very large, but very quickly goes to very close to zero and doesn't really deviate from this for most times. Yeah, that's the picture here. There are very strict results on this. We can bound the equilibration of observables by a quantity that depends on the largest eigenvalue gap of the observable that has support on the original state. And then something called the effective dimension, or the inverse participation ratio, if you're familiar with this, which is to do with how many energy levels the state is supported on when you start. Yeah? And this is a strict bound as to how much this deviates. And likewise, so this is for an observable. We can make similar statements about how far the system deviates for if we look at a subsystem only. And that's in the A here is the dimension of a subsystem. We're thinking of subsystems A and B. It's an observable in the line above. Yeah? So as a dimension, the ratio of the dimension of the subsystem over the effective dimension, the inverse participation ratio, this also becomes very close. If we look at the local state versus the traced out state over the global equilibrium. Yeah? That's a standard established notion of closed system equilibration, and that's what we want to look at. A point to make here quickly is that equilibration is very strictly and strongly larger than thermalization. We could not hope to achieve anything like this with thermalization. That's a many-to-one mapping once the temperature is fixed, and there cannot be a measurement record in this case, right? So we're interested in equilibration, which includes thermalization, not in thermalization. This is an important point. And the other point is that everything's still unitary. We're just asking about an effective, what does the system look like, right? How distinguishable is it from the equilibrium state? And these bounds tell us that it's not going to be very distinguishable, loosely put. Yeah? And so in this equilibration, what we want, as I've already said, we want the system to go to an SBS state. We can derive a form of the Hamiltonian. This conditionally sort of rotates all of the environments, observer systems, depending on what state it finds the central system, the one that's being observed in. And what we can show that under this condition, this is the first negative result, this equilibration could never happen. Yeah? And you can actually spot this directly because the SBS state is very rank deficient. It does not have any support on those subspaces where different observers disagree, yeah? Which is a much larger subspace than the one where they agree. So, okay, exact equilibration doesn't happen. It doesn't even equilibrate to a classical quantum state. But maybe this is not what we need anyways. We need to be able to get there very closely. And the result there is going to be that, yes, this does happen, so we can start with a similar type of Hamiltonian, and we want to get to an SBS state, and how we can get there is by looking now at coarse graining over environments, meaning grouping many of these really small, say if they're all qubit systems, we take them in groups, and as we increase the dimension of the systems involved, this exponentially, the fidelity between these parts exponentially decays, so we get arbitrarily close to the SBS state, to an objective state of affairs in the dimension in the coarse graining. Yeah? So that's neat. This works. The caveat is that it requires this type of Hamiltonian up here. The next question that I want to answer is, this objectivity is the standard form in which people think about this. It's named this for historical reason. One could argue that maybe intersubjectivity would have also been a good term from the start. What we just talked about is called objectivity. We can go to something else called intersubjectivity. By asking first, we're in a thermodynamic context here, so we could first ask what happens if we put the environments, rather than looking at a large pure state, what happens if we put the environments into an initial thermal state, each of them, right? And then we could also ask what happens if we don't really care what happens to the central system after the measurement, right? This is not typically in the case of objectivity. You look at the correlation in the sense of a mutual information between the central system and any of the observers. What about if we just care for the observers, yeah? Those are the two steps that we're going to take in the second piece of work, which is the top one down here. And without going into the exact details, there's three things that we might require for ideal intersubjectivity as opposed to objectivity, right? The first one is we want a sense of locality, meaning that the outcomes are accessible locally to the many observers that look at the system. We want a sense of probability reproducibility, which is to say that if any of the observers queries what state is the central system in, that probability should coincide with the probability that under standard measurement description that we would have assigned to the central system. And the last one is, of course, they should agree. We wouldn't want to call it intersubjectivity if they don't agree, which we can measure as this is a projector on the agreement subspace as the support on the agreement subspace. Yeah? And there's a much larger subspace as before where there is no agreement. Yeah? So this is what we get. In the ideal case, there's a theorem by Ozawa which says that actually if we satisfy the first two perfectly, agreement comes for free. It's implied by those. Yeah? And another thing to note is that as before, what we get from this condition here is that we require this again to be in a rank-reduced state. And we can already see that this is not going to work so well if we start in thermal states, right? And so to do away with this ideal requirement, we again need to give something up. It doesn't come for free. And what we're going to give up is we'll allow for a bias. We'll want to not have a strong bias, but that's the sort of trade-off. And in particular, we'll want the individual observers to have the identical probabilities of individual results, but they don't need to match what we would have previously had on the system. Of course, we want them to get close, right? And then we can also quantify the agreement, and this is again just this, measuring the support of the state on the subspace of agreement. And what we get from this is we can first get an upper bound on the agreement, which scales with the temperature, and then we can get a lower bound, so we can constructively give an equation for the amount of agreement that we get for a given system with given environments. And we can then bound what the optimal bias, how little bias we can get away with for the optimal case of agreement in this situation. Yeah? And so the gist is that the morale of this is that, again, coarse graining will save the day, and this is what we expect in a way. It's nice to see this sort of properly, right? So as the observers become more macroscopic, we see that very rapidly they will actually find themselves in agreement. And this is what you can see. The red line is the bound that we get, and the blue line is the agreement. And you see this goes to very small values very quickly. And at the optimal case, we can also plot the bias, which goes to even smaller values, right? So we've given up originally. We said we'll allow for this bias, and that seemed like maybe a strong trade-off. But what we can see in practice that as soon as we start coarse graining, grouping systems together, this is not much of a concern. It becomes very small very quickly, right? It's a number between 0 and 1, as is the disagreement as well. Good. With that, let me sum up what the main points are. So the first one is a question or a hypothesis. Can we think of measurement in quantum theory as a result of a thermodynamic process and as a result of equilibration in particular? The first result is that this does not happen exactly. And we're not so surprised by this, but it's good to note that, yeah? The more important result is that very quickly, as we group systems together, as we make the observers macroscopic, we recover a sense of objectivity from equilibration. And then in the second part, we dropped the non-disturbance requirement, and we went from a notion of objectivity to a notion of intersubjectivity, where the central system becomes less relevant, and we also introduced thermal environments. And what we noticed then is, again, for the same reason, to do with rank deficiency, we cannot have ideal intersubjectivity in this case. But we can similarly approximate it under coarse graining and, of course, also by cooling. Yeah? So if we go closer and closer to 0 temperature, we approximate the ideal state of affairs again. Yeah. So with that, let me thank my collaborators over here. You can see the references up here, and you'll recognize at this point 3/4 of our group here on the picture. You've already seen Kuva and Yutong speak. So thank you very much.
Thank you very much, Felix, for the talk. We have questions here.
Very nice talk. So I guess like many people in the room, I'm not used to thinking about objectivity. Mm-hmm. So can you just maybe go right back to the beginning and unpack a little bit what something that's not objective would be? It might help me understand what it means. So I guess you had this formula which had bra J, ket J. I guess the most general state, it would be I and J because you would have superpositions. Mm-hmm. I guess that's the most general state you could have. Otherwise, I'm not sure. Anyway. So if you have superposition like this, how is it not objective, or what consequences would you see?
Yeah. Let me take a quick detour to answering this question, which is, I decided to remove a slide from here in the interest of time, but maybe this is actually useful exactly to answer this question. This is the normal picture. This is a very standard picture in quantum Darwinism that illustrates objectivity. And in particular, it compares two types of states. So the red one is one that shows objectivity. The green one is a typical AHA random state. So what does this show? You're looking at the mutual information between the system and some proportion of the environment. The proportion goes from 0 to 100%. Down here. As you increase that proportion, at some point the mutual information goes to 2 because it's a pure state. If it were mixed, it would go to somewhere around 1, right? So what you would get in the best case is that if the mutual information is perfect, you get to, so if the environment has all the information in it, that fraction of the environment, if that has sufficient information in it, you equal to the entropy that you assign to the central system, right? And so for an objective state of affairs, this happens very quickly as you group environments together. Whereas for a AHA random state, this happens for a very long time. You keep on combining environments, and you learn the environments know very little, unless you get to until you get to about half of the observers, and suddenly they jump to very high. Yeah. So this is one way of answering this. This is not exactly the notion that I was presenting, which is why I skipped this or removed this slide. But maybe it gives a good idea of how this works. We're looking at this more specific version, which is at the state level, right? Rather than at a level of mutual information. And the reason is that discord can hide in this, where we describe specifically the state on each observer system, and that tells you how much the observer can learn directly from looking at it. It's effectively via this requirement down here. Does that answer the question, or at least make some way towards answering it? Yeah?
Yeah, I also have a question on objectivity. Actually, on the slide you show on the appendix. So I have already seen this curve, and the thing that confused me is that I understand the intuition that at some point you get a plateau. I also understand why mathematically you should get to 2HS, but physically, I don't understand. Like, to me, if it was an objectivity, it should remain as a plateau forever at some point, or maybe increase a little bit. I understand that mathematically it's not possible, but it makes me wonder how are we sure that this model is good? Because there is a kind of, to me there is a kind of contradiction for f equal to 1. You see what I mean?
Yeah, this has to do with entanglement and discord as well, and the way that quantum correlation. So if this were classical, this would max out over here, right? It wouldn't have this final peak, and that's not something to worry too much about. Physically, you can think you're never going to look at the entire thing. Just forget about a part and stop the graph somewhere over here, right? But where this comes from is just from the way in which these entropies behave. So if you want to correlate it, this entropy vanishes at some point because you're in a pure state. And these entropies are whatever they are.
Okay,
right?
Thanks. Yeah, I understand mathematically, but it's just that for me physically, I have a hard time to interpret the one limit, but I understand that you should have it mathematically.
And this is a good point, and it's part of the reason why we want to look at the state structure instead of this picture, because it does hide some quantum correlations. It's not clear what you can actually access locally. The mutual information is a fine measure, but it does have some properties in the quantum case, including to do with discord, that are not very neatly interpretable, exactly in the way that you're saying. That's why we prefer looking at the SBS structure, which we can also motivate axiomatically directly.
Thank you.
Yeah, go ahead, Fede, and then here.
So there's high chance that I'm completely wrong, but somehow my intuition tells me that this should be relatable to some hidden variable models, so maybe to contextuality or to Bannon locality, or somehow the framing is similar. Do you have any notion of this?
That's a good question. I've not thought about it in this case. So this becomes a classical correlation in a way, right? So these are classical quantum states. If you look at this thing, this is a classical correlation. So you're imprinting the measurement record onto the environments individually or onto the fraction.
Sure. There's so for example in contextuality you still try to see if the to assign a probability distribution to all possible outcomes and all possible measurement scenarios, and then you fail to assign up.
I think if this were contextual, you wouldn't find agreement, right? Is maybe one way of putting this. Yeah.
But normally you also fundamental requirement for all these scenarios is that you need non-commuting observables, whereas here you don't really need this, right? You measure one specific observable.
Yeah, so I guess the program is really, so you have some information encoded in the system centrally, which you want to encode classically. The question is how, that's the measurement problem, right? We look not at the measurement problem as such, at this more nuanced version of objectivity, but this is a classical information that you ultimately want to get on the environments and between observers. So in a sense, there is no quantumness to the outcome that you want to have, right? Once a measurement has happened, it shouldn't be context dependent among observers, what they think they have seen, etc. But you can think about alternative ways to construct paradoxes, etc. in Wigner-Friend senses, etc. But here, that's really not the program, and it's not what we're looking for. If you want to explain measurement in quantum mechanics, it's the output that you're looking for is classical information, right? I hope that answers the question.
It sharpens it, but I'm not sure if I got it completely.
Yeah, here. Thanks for the nice talk. Regarding this coarse graining, you mean the grouping of the small observer into? Yeah. So how do you choose the groups? So is it random? I can take a subset of a proper size, and this is enough? So among all?
Yes, this is typically done randomly. So both in the picture that I showed afterwards with the plateau, this is done randomly. You can do this randomly here. You can also pick them in a sort of worst case scenario. You can make adversarial sort of models to this, where you pick very specific Hamiltonians that put all the information somewhere, and you need to group them in a particular way. But you can see that this, for the generic case, this decays very quickly.
Yeah, so regarding the decay, the last question, do you consider here like a time scale at which this broadcasting happens? Because at some point I wanted to define like a time when a measurement happened, and I think it's a good
Yes.
way to define it. Did you study the?
So this is what you're asking is one of the sort of most important questions to ask here, right? How quickly does this actually happen? Is this a hypothetical thing? And this is why I was stressing this bit, that this really happens very quickly, even though we define some infinite limit. So this model here isn't a model that comes naturally. So what you shouldn't expect is that you take a quantum lab and you look at it, and if you just describe it right, it looks like quantum measurement has happened. This should be an extraordinarily unusual state of affairs, right, for this to happen. In part because not all of the environments are measuring each other. There's a privileged system, which is the central system. But so quantum measurement is a very unusual state of affairs, right? We're really picking a system that we want to observe and that we want to make a record of, right? It's not this is not a generic thing to happen, but it does raise the question as to what's a good interaction that gives rise to this. And we've been looking at this, but this is a not fully concluded research program, let's say, to figure out it can be in a physical model, it can be kept those times. But I want to stress that these are very short usually, even though they're described in the infinite limit. But if you use any model that people would have been using for these are typically very short.
Right.
Yeah?
Thank you.
Yeah.
Okay, I have a very quick question. Can you give a little bit of intuition under the fact that more macroscopic observers like help us go towards intersubjectivity? Like, what is that? Is it that Hilbert space is growing, or is it like redundancy that's giving us this like approach towards?
Yeah. So it makes it a little bit easier to. There's a finite set of probabilities to do. So this works in infinite. Everything I've described here works in infinite dimensions, but I haven't insisted on that, right? But so there will be whatever dimension of the central system here will dictate how many agreement subspaces there are. For each potential measurement outcome, we have an agreement subspace. And so what thermality does is it spreads your probability distribution over everything. So you need to group things together. They need to collaborate to find the right subspaces.
Okay.
Yeah?
Okay. Thank you. Okay. If there are no more questions, we thank the speaker again.